In this video, we are discussing GATE 2005 EC question related to Nyquist plot. So it says that polar diagram of a conditionally stable system for open loop gain k is equal to 1 is shown. The open loop transfer function of system is known to be stable. So we have to find the condition for stability of closed loop system for various values of k, and these are the four options given. So this is the Nyquist plot. This plot is minus 0.2, this point is minus 2, this is minus 8. And so this is the question. So first, please note that the polar plot does not give absolute stability, but the Nyquist plot and Routh-Hurwitz criteria give absolute stability. So we have first to discuss the Nyquist stability criterion. The Nyquist stability criterion is n is equal to p minus z. So n is the number of encirclements about critical point minus 1 plus j0 in anti-clockwise direction. P is right hand poles of open loop transfer function. Z is right hand poles of closed loop transfer function. So this is the Nyquist stability criterion, n is equal to p minus z. And this is the Nyquist plot which we are given. Here we are not given the point k in this plot, but we are given that k is equal to 1. So we can simply multiply this by k. So what we get is this. Simply multiply k with all these points. So this is minus 0.2k, this is minus 2k, this is 8k. And this Nyquist plot starts from omega equal to 0 at angle minus 90 degrees. So we can say that it is a type 1 system. So I have drawn the polar plot for this by using the mirror image. So this is the mirror image. And this is the circle. Since there is a type 1 system, so there will only be one circle. So the question says that open loop transfer function is stable. So p is equal to 0 because p denotes the number of right hand poles of open loop transfer function. So open loop transfer function is stable, hence p is 0. Now there can be four possibilities of the critical point. Critical point is at point A, critical point is at point B, critical point is at point C, or critical point is at point D. So we have to check for all these four possibilities. If I take critical point at point A, then the number of encirclement of critical point will be this one and this whole. So there are two encirclements of critical point. One is this small circle and one is this big circle. And these both are in clockwise direction. So the n, which was the number of encirclement in anti-clockwise direction. So these are in clockwise direction. So the value of n will be minus 2. And as per Nyquist stability criteria, n is equal to p minus z. So minus 2 is equal to 0 minus z. P is equal to 0 as we have already seen. So the value of z will be 2. So the system is unstable because the number of right hand poles is 2. So case 1 is unstable condition. And we can see that the Nyquist gives absolute stability because it says that this system is unstable because of two right hand poles. So Nyquist and Routh-Hurwitz provide absolute stability. Polar plot provides only relative stability. And note that when we solve for z, then if we are using the right approach, then the value of z can never be negative. So I take case 2. In case 2, there are one anti-clockwise encirclement and one clockwise encirclement. This small circle, for case 2, this point is B. Then minus 1 plus j0 critical point lies here. So there is one anti-clockwise encirclement and one clockwise encirclement. So the total number of encirclement will be 0 because one is clockwise and one is anti-clockwise. So it means n is equal to 0. So if n is equal to 0, p is equal to 0, so z equal to 0. So the case 2 denotes the stable system. And in case 2, the critical point lies between 0.2k and 2k. So using this we say that 2k is greater than 1, and so the value of k will be greater than 1 by 2, and 1 is greater than 0.2k, so k is less than 5, because the critical point minus 1 plus j0 lies between 0.2k and 2k. So the value of k will be either greater than 2 or less than 5. So 1 by 2 is less than k is less than 5. This we have got. So already we have got our answer. Our answer is answer is option B. We can see that in the option B this criterion is given. But we will solve further. So case 3 is point C. In point C again there are two clockwise encirclement. See, if the critical point is at point C, then there are two clockwise encirclements. One small, this one, and one big, this one. Big one, this big circle, and one small circle. So it is similar to point case 1. Two clockwise encirclement. So n is equal to 2 means n is equal to minus 2 means z will be equal to 2 plus 2. So again unstable system. Now let us check for point D. If critical point lies at point D, then we can clearly see that point D has no encirclement. So n is equal to 0 for point D. You can see point D has no encirclements. So if critical point is at point D, there are no encirclements. So the value of n is 0 and the value of z is 0. Hence this is the stable system. And we can say that 1 is greater than 8k, because this is 8k, and if this is the critical point, then 1 is greater than 8k. So k is less than 1 by 8. This is also given in option B. We can see that k is less than 1 by 8. So option B is correct answer. Thank you. For any feedbacks and comment, please leave in the comment box below. Please like, share and subscribe the channel.